Yeah, thanks for inviting me. And also, I should start by confess that this is a lower bound talk, but the MPC here is not multi-party computation. It's massively parallel computation. So I'm doing lower bound outside crypto. Yeah, so what I do is just using crypto technique that we have, and then try to get a lower bound in this massively parallel computation model. So probably people are not familiar with this model. So this model is about 10 years old, and it's become a popular model in the algorithm community to study parallel computation that kind of capture our current computation model, like Hadoop. So let me just start by introducing the model. Oh, by the way, this is joint work with Guan Yi, who is my former student, and Xiaorui, who is the guy actually doing MPC algorithms. Yeah. Yeah, so let's start with the model. So this is a model, I think, defined by Karlov like around 10 years ago. So let's consider that we have all the data, say, on the cloud, and we need to do computation. So we kind of spread all the data, distribute all the data to some local computers. So the data is so large that no local computer alone can store the whole data. So you need to split it in some way. After you split them, then these local computers will do some local computation on the local data they have. And then at the end, they will generate some output. And this will be collected again for the next round. So in this model, if you only have one round, you cannot do much. So people consider doing this process for multiple rounds. So you repeat this process of distributed data, do local computation, aggregate data, and so on. In this way, you carry out parallel computation. So it's kind of a clean model. So what kind of parameter do we care about? What kind of complexity measure do we care about in this model? So there are not many parameters. So first of all, you have your data. Let's say the total input size is n. And you have this local machine, which has certain amount of local memory. So the space per machine is denoted by S. And also you have the parallelism from you have multiple local machines. So the number of machines is called M, which is also the level of kind of parallelism you can have in this model. So what do people care about, and what's the typical parameter setting for this model? So typically, as mentioned before, we don't expect a local machine to be able to store the whole data. And if that's the case, the local machine alone can just carry through all the computation. So we usually assume S is less than N. But all the machine in total should be able to process all the data. So we usually assume S times M is order N. So it's typically that people consider cases where kind of order N is enough for the computation. But sometimes you can maybe have more machine, so you get like N log N or something bigger. But usually people study machines problems that can be computed in about linear space. And typically, this parameter S and M are assumed to be polynomial in N. So usually S and M could range from N to the epsilon to N to the 1 minus epsilon. And usually, on the algorithm side, the algorithms are required to work for all these parameter range. So you get a smooth trade-off for kind of the amount of parallelism and the work you need to do per machine. And in this model, people care the most about the round complexity. So how many rounds do we need to finish a certain task? Because typically local computation is much faster, and the overhead comes from this kind of communication of the input or your data.
What communication complexity per round?
Yeah, so people try to not to model this, not to care about this too much. So you can send any amount of message to anyone, but you only have a local space S. So in some sense, you can only expect to receive all the S bits from all other parties.
So can we assume without loss of generality that each arrow is of size S? Or it is with loss of generality?
Yeah, without loss of generality. It's upper bounded by S, yeah.
So you get S bits, essentially somebody encodes for you, even for the servers, then they do local computation, somebody decodes and re-encodes. So this like big cloud thing is for free?
Okay, so usually, I mean, they care about algorithm, right? So the algorithm will just specify that I send some information to some other machine, and I will expect to receive some data from another machine, and then they don't care about the details of the modeling, other than that in this algorithm specification, you only get not too much messages per round.
I mean, the
Yeah.
cloud between rounds, that's just routing.
Yeah, let's just routing.
Some messages go from, there is no computation in the yellow clouds.
Yeah, there's no
Just
computation.
messages go from some party to another.
Right. It's just the machines sending message to each other. Yeah, so in this model, people usually want to do things in constant run. And for them, like all the log n run is maybe kind of okay, but log square, they already consider it to be too slow. Yeah, so, okay, so this is a model that they try to capture this MapReduce paradigm, Hadoop, etc. But as you can see, the model actually omits a lot of detail and only focus on this simple 3 parameter and the run complexity. So they omit like the map step or reduce step in the MapReduce, but just care about the number of rounds you need. So in this model, people ask what kind of problem can be solved efficiently in the sense of a small number of rounds. And over the past maybe 10 years, there are lots of nice algorithmic ideas. So stuff on like divide and conquer, it's easy to parallelize in this model. You just divide until your problem fit into a single machine, and then the machine will solve it for you. And then greedy is maybe more sequential, and then also this dynamic program is like sequentially filled in a table, this kind of thing. But they all like try to do this either exactly or approximately in constant round or logarithmic number of rounds. So there are lots of nice algorithmic ideas there. So yeah, it's a popular, clean theoretical model for parallel algorithm design. And I think it's good to compare this model with the period model, another kind of standard model for parallel computation. So I think one difference here is that in the period model, you have a large shared memory where all this small CPU can access to. But in the MPC model, each machine has a certain decent size of local memory, but there's no kind of shared memory. So I think this is maybe the reason that period is not popular, because in reality, getting a shared memory architecture is quite expensive. On the other hand, in the period model, you allow for arbitrary number of CPUs, or arbitrary number of CPUs, so you can have high parallelism. But in this MPC model, you get the bounded parallelism. So you only get M equal to kind of n to the epsilon amount of parallelism. And also you have a restriction, typical restriction on the total space. And I think another aspect that's very different is that in this MPC model, it's kind of hybrid in the sense that in one round, one machine is allowed to do arbitrary amount of local sequential computation. So that makes it also very different from period, where in one round, a CPU can only do kind of one step of computation. And they focus on this round complexity. And because of this, for example, sorting, you can do it in just a constant number of rounds, and that's kind of one of the reasons that they say that this MPC model is better than the P-run model in practice. Okay, so this is, this the way I understand about the MPC model.
What is the name? It's a collection with multi-party computation. Which one is going to emerge as a
Yeah, so you need to bear with me. I'll try to confuse you as much as possible in my talk to keep calling it as MPC. But yeah, you can design MPC for MPC. Yeah, okay, so lower bound. So what do we mean by lower bound for MPC model, and what do we know about it? So here, the lower bound refers to problems that cannot be parallelized well in the MPC model. And let's just look at one example. So let's consider like graph connectivity problem, where given a graph, you need to decide whether it's connected or it has multiple connected components, or even a special case where you are given a graph, you are promised that it's a big cycle or just two disjoint cycle, and you try to distinguish them. It's not too hard to do this problem in log n round. However, I think it's an important open question in that community that whether this can be done in constant number of rounds.
So is that like essentially information theoretic lower bound? Because it doesn't matter what the computation does.
Yeah.
This is about communication.
Yeah. Well, not quite actually. So let me just get to this point. Yeah. So for because you want your problem to be in P, so that's kind of the reason that complexity comes in. So there's unconditional lower bound by Rough-Garden et al. They show that there's some problem in P that require log S n number of round, where again n is the input size and the S is the local memory size. So for the typical parameter setting where S is polynomial in n to the polynomial in n, this is only a constant round the lower bound. And the reason that we cannot hope to further improve this lower bound is that once you get too many rounds, you are ready to be able to simulate NC1 computation. So a hardness will imply a separation between NC1 and polynomial time. Yeah, so they show in this sense the unconditional lower bound they can get is the best you can hope for.
This is like, it means that if you can prove it for just one problem, so if there is one problem, then NC1 of the code will be. Sorry, I'm just trying to.
Sorry again?
What is it quantified? Is it for all problems? The super logarithmic lower bound?
Oh, there's one problem. They design a hard problem. Yeah.
So if there is just one problem, it means the problem is not an NC1.
Yeah. That's essentially what we do, but I'll go talk about it. Yeah. Yeah, so there are also some other lower bound for graph problems that shows lower bound for restrict type of algorithm that people usually work with, or conditional lower bound that assume graph connectivity requires omega log n round, and then they show something that's also requiring log n round. Yeah, so that's kind of exactly what we do. So we say that, okay, given we don't know how to prove unconditional lower bound, and we are crypto people, we have so many tools. So let's try to prove conditional lower bound using crypto. So so essentially what we do is to try to define a hard problem in the random oracle model. And that's essentially some point tracing problem that I'm going to talk about. And now the goal is, again, try to say more precisely what do we mean by a problem that's hard to be parallelized well. So we want to design a problem that can be computed in time t by a RAM program. But we want to show that any MPC algorithm that can compute this function would require some large FT number of rounds that's much bigger than log n. So once we do that, we can interpret the results in this way by, say, we just instantiate this random oracle by a cryptographic hash function. Then we get some concrete plane model function that can be conjectured to be hard for MPC. So if your hash function requires th time to compute, then you get a function that can be computed in t times th by a RAM program, but will require like some high number of rounds in this MPC model. And so in the actual construction, because the way we use random oracle is kind of very natural, so kind of we don't expect this random oracle heuristic to fail in this particular case. I mean, otherwise it's also nice, then we'll get a very natural counterexample for random oracle heuristic. So it's likely that you can interpret it as a negative result for MPC, that there is indeed exists some concrete problem that cannot be parallelized well in MPC model. And in terms of the concrete parameter we get, we can show that this function that compute both in time t would require omega tilde t number of rounds for any polynomial t. So this is kind of best possible hardness you can get for this model. Yeah.
Is it clear that if the number of rounds is unbounded, any computation can be simulated?
You mean second?
Let's say you have some linear time, linear space computation, but now you do this, you put it into this model, can it, if you don't care about the number of rounds, can you always simulate?
Yeah, I think in one step you can simulate a RAM, one step of RAM program, right? So, yeah, so I should say this. So if this problem is computable by a RAM program in time t, then you can do it in t round in the MPC model. And even with a very small local machine size, S can be just polylogarithmic. Yeah, so let's so let me just start to define this half function concretely. So before defining it, I want to draw a comparison to this memory hard function, because it's kind of share a similar type of hardness in the random oracle model. So in this memory hard functions, it also, shows that some function that can be computed easily or more efficiently if you have enough space, but it will become harder if you don't have enough space. So this is kind of similar hardness we are looking for this MPC model, where you need a multiple number of rounds because your local machine cannot store the whole input. Okay, but the kind of the complexity we care about is different, in the sense that here we care about round complexity. And again, in one round, the local machine can do arbitrary sequential computation. But in the MHF setting, we care about adaptive query complexity. So it's a lower bound on the number of adaptive query. So that's still kind of different. But nevertheless, yeah, as Christos said, the intuition is that this kind of point tracing function should be hard. And that's what we try to do. But we set it up in this to tailor to this specific model. So let me just define the function. So I call it a line function. So here my input x, I view it as a vector of v element, each of length u. And okay, so now I'm going to define how this line function computes its output. So we start with x1 and put some initial, say 0, and feed it into RO to get some output R2. And then just iterate. So next time I take x2 and R2 and feed into RO to get some R3. And then I just continue. And at step I will use xi mod v. So basically I'm using my input in a cyclic way to fit into, to select as the input to the random oracle, and use the Ri I get from the previous step to fit into RO and get I plus 1. And at the end, my function will just output the final point, RT plus 1. So it should be very intuitive that this function should be hard to compute. I mean, you need a lot of sequential space. Yeah, but let's take a closer look. So basically, you want to use this model to compute this function. And because it's a random oracle, intuitively, you need to kind of compute this function by really making the query in sequential order. You cannot jump. And when you make a query, you will need the input x1, x2, and x3. But now a local machine with space S cannot store the whole X. So it can store, intuitively can store S over U number of points of X. And that would only allow a machine to advance for S over U number of nodes in the line. So intuitively, and the multiple machine doesn't help because they need to, I mean, each of them only has a small bounded memory, and each of them can only, in one round, advance S over U number of points. So in one round overall, they can still only advance S over U point. So intuitively, you would take T divided by this number, so it's roughly T divided by S, number of rounds to compute this line function. So this is not the omega tilde T bound I promised before. Somehow we need to still make this problem a bit harder. But let me focus on this simpler function first, because the analysis of this would be very simple using compression argument. I mean, much simpler than in the Lucas case, actually. Yeah, so let's.
But if U and S are in the same order, since you already have the omega T lower bound.
Yeah. But you want to get let me see. So you are saying that using a larger oracle, I think if your random oracle take a long input, then that would also require much large time to evaluate. So when you instantiate it, say here, this will be a large number. So I still want to use a small random oracle to get a concrete instantiation with large gap. Yeah.
So you would like the input to the oracle to be something like polynomial like this?
Yes, yes. Yeah, so since the proof is not hard, so let's just do a 2 slides proof for it. So here, this slide is actually very simple, although there are some notation. Here, I just want to formalize the statement that you need to query the random oracle point by point to evaluate this line. So this Tj is just so at the jth round, what's the information this MPC algorithm know about this line. So Tj will be the maximal index I, where the sum of the machine knows the point at the ith point of the line. And the jump just says that this event just says that the machine happened to be able to query some point I, but without querying some earlier point that it doesn't know. And it's a simple exercise to say, just because of unpredictability of random oracle, that the chance that this jump event happen will be negligible. Okay, so now let's.
Does it use compression or this is elementary?
This is elementary, and then this is preparing for using compression. Actually, so I should maybe mention that although this kind of harness is very intuitive, somehow we don't know how to directly formalize it without, or prove it without using compression argument. So I mean, intuitively, the issue is that we don't know how the machine store information in their local memory. So it's hard to quantify what does the machine know at any point of time. What's the point X he knows, because he can maybe do some complicated encoding. But somehow, yeah, so initially we didn't try to use compression argument. We tried to use some more direct information theoretic analysis, but we just don't know how to do it. But once you use compression argument, it becomes kind of super simple. Yeah, so now with this definition, so it's kind of, this TJ again measures how much you know already on the line at the end of J's round. So this lemma just says that in one round, I can only learn roughly S over U number of points, up to negligible probability. And this lemma can be proved. Now I'm going to use compression argument in a kind of very straightforward way. So let's do it. So, okay, so the key point here is that because the machine cannot jump, suppose Tj is greater than Tj minus 1 for quite a lot, there must be some machine M that queries this point between the line from Tj minus 1 to Tj, kind of point by point. And this query itself kind of reveals that this machine knows the loss point. So it's kind of, we said that it's not clear how to formalize the machine knows what the machine knows from store in its local state. But this algorithm itself actually kind of decodes the information for you. Yeah, so because of this, if the machine can query the line for too long, means that the machine knows too many input xj, xp, more than the space that of his local state, then now we can use this machine to compress both the input and random oracle. And it's simple, we actually don't compress the random oracle, we just store the random oracle as it is. And for the points, the input that's outside this window of Tj minus 1 to Tj, we just store it. But then we will store mk initial state sigma at beginning of the round J. That would help us to kind of, by rounding mk would tell us those xp's in between this interval. And so we just need to store the index, which query mk make is this xp. And by doing so, and we can decode this, again, simply by just running mk and look at the index to reconstruct all the missing entries of the input. So it's very, very simple case of compression argument. So just looking at the parameter, so we need to pay S bit to store the state sigma. But for each of the xp, instead of storing this xp, the U bit of it, we only need to store the index of which query this machine make is xp. So you only need to use log q bits to kind of describe this xp. So you save u minus log q bits, where q is the number of query of the random oracle. And this, you save it for each xp. So this would, I mean, a simple exercise would translate to that the machine cannot be able to advance for too long in one round. So I have 3 minutes. Yeah. So yeah. So as I mentioned, the problem so far we got a lower bound only roughly t over s. We want a lower bound that's independent of s. It's omega t over t. So we need to make it harder. And the way to make it harder is also quite simple. You just instead of picking this input xi in order, let's just pick a random entry using random oracle. So now my random oracle would not only give me R2, but also a random index L2 that specifies which input I'm going to use for the random oracle. So intuitively, as long as S is not too large, I can only store, say, half of X. Then each time I'm lucky that this the next input is in my memory is only a half. So say after log square number of step, I mean the chance that I can advance for log square step would be negligible. And this will give me the desired hardness for MPC. However, of course, it's tricky to argue this probability amplification directly because there's no independence at all. And we need to somehow try to kind of emulate this kind of probability amplification in comparison argument. So this might be a bit interesting trick to the comparison argument. So I won't go into detail here, but I'll just sketch that the main idea here is to run MK sigma not only on the random oracle itself, but on a bunch of modified random oracle that allow me to kind of force MK to decode more information from sigma for me. I think this was used before for memory hard function, but we do it in different purpose. So by doing so, basically I just enumerate all the kind of log square step or path of the index. I modify the random oracle for the future index. And then I just run through list MK for all possible paths and collect all the kind of the queries that MK reveal for me. And then I use this B to do compression. So just intuition, if MK knows too much, so you get a large size of B, then I can use it to compress. I get contradiction. But if MK cannot know too much entries of my X, then the chance that the MK can kind of, I mean the fraction of random oracle that MK can continue for double step will decrease exponentially. So that's roughly the idea, and you can formalize it. So that's all I want to say about the proof. So I think it's just actually a simple idea. Just try to use crypto technique to give lower bound in other contexts. And what we do is in this MPC model. Again, it's a popular model for parallel algorithm design. So I think maybe the interesting message is that somehow we can get the best possible kind of hardness here. We get for any t, we get a problem computable in time t, but require like almost linear in t number of rounds in MPC. So it's this function that cannot be parallelized. So just one question also, I guess one natural question is, okay, we are looking for conditional result anyway, but do we really need the random oracle? Can we replace it by some other crypto or complexity assumption? And that's it.